Right now, somewhere in the world, an Uber driver just accepted a ride. In the next 200 milliseconds, Uber has already done several things simultaneously. It calculated a route. It updated the driver's GPS position on the rider's screen. It adjusted the surge multiplier for that geographic zone. It logged a dispatch event to its data warehouse. It notified the payment processor to pre-authorize the rider's card. And it sent a push notification to the rider's phone. All of that in 200 milliseconds across a distributed system that processes 14 million trips every single day. Today, we are going to reverse engineer exactly how Uber built that system. The event-driven architecture powering it, the Kafka pipelines behind it, the real-time location streaming making it possible, and the engineering lessons you can take directly into your own distributed systems work. Let us get into it. The scale problem that broke the monolith. Let me start at the beginning of Uber's architecture story, because understanding the problem they were solving makes every decision they made feel not just logical, but inevitable. In the early days of Uber, the platform was a monolith. One application, one database, one deployment. This is completely normal and completely reasonable for a startup. When you have 1,000 users, you do not need distributed systems. You need to ship features fast and iterate quickly. But Uber grew at a rate that very few companies in history have experienced. From 2010 to 2015, they went from a small pilot in San Francisco to hundreds of cities across the globe. The number of concurrent trips went from hundreds to hundreds of thousands, and the monolith started to break. Here is what breaking actually looks like in practice. When you have a monolithic application, every service is tightly coupled. Your ride matching logic is compiled alongside your payment processing logic, alongside your driver location tracking logic. They all run as a single process. They all read from and write to the same database. This creates what engineers call a cascading failure pattern. If the database query powering the driver location tracking service starts running slowly due to a spike in write traffic, it holds up the shared database connection pool. That connection pool exhaustion starts affecting the ride matching service. The ride matching service slows down, which causes retry storms from mobile clients. Those retry storms increase database load even further. And within minutes, a problem that started in location tracking has brought down payment processing, ride dispatch, and driver registration simultaneously. Uber experienced exactly this at scale. They needed a fundamentally different architecture. One where a failure in location tracking could not bring down payment processing, where a spike in ride requests during rush hour could scale independently from the driver registration service, where individual services could be deployed, scaled, and failed completely independently. The solution was to decompose the monolith into microservices and to connect those microservices through an event-driven architecture. Apache Kafka was the backbone of that entire transformation. Event-driven architecture fundamentals. Before going deep into Uber's specific implementation, let me make sure the core concepts of event-driven architecture are completely clear. Everything else in this video builds directly on these foundations. In a traditional request-response architecture, services talk to each other synchronously. Service A needs data from Service B, so it sends a request directly to Service B and waits for a response. This is how RESTAPs work. This is how most engineers design their first distributed systems. The problem with synchronous communication at scale is coupling. Service A now depends directly on Service B being available. If Service B is slow, Service A is slow. If Service B is down, Service A cannot complete its work. At small scale, this is manageable. At Uber scale, where thousands of microservices communicate with each other thousands of times per second, synchronous coupling creates a reliability disaster waiting to happen. Event-driven architecture flips this model entirely. Instead of Service A calling Service B directly, Service A emits an event. It publishes a message to a central event stream that says, "Something happened, I am done." The event contains all the data describing what just happened. Service A does not wait for a response. It does not care who is listening. It publishes and moves on. Service B subscribes to that event stream. When a new event arrives, Service B processes it on its own schedule. If Service B is temporarily slow, events wait in the queue. If Service B is down, events accumulate and are processed when it recovers. The two services are completely decoupled from each other. Neither one needs to know the other exists. This is the fundamental architectural shift from synchronous point-to-point communication to asynchronous event-based communication. Now, there are three key components in every event-driven architecture. The first is the producer. This is any service that generates events. A driver accepting a ride is a producer. A payment being processed is a producer. A rider submitting a rating is a producer. The second is the event broker. This is the infrastructure that receives events from producers and stores them reliably until consumers are ready to process them. In Uber's case, this is Apache Kafka. The broker guarantees that events are durable, ordered within a partition, and delivered reliably. The third is the consumer. This is any service that reads events from the broker and acts on them. The pricing engine consumes location events, the notification service consumes ride status events, the fraud detection system consumes payment events. The real power of this model is extensibility. You can add new consumers at any time without touching any producer code. When Uber added their driver analytics product, they did not need to modify the ride dispatch service at all. They simply added a new consumer that subscribes to existing ride events. That is clean architectural separation. Kafka, the backbone of Uber's architecture. Now, let me explain Apache Kafka specifically, because understanding how Kafka works internally is essential to understanding how Uber's system functions at the scale it does. Kafka is a distributed event streaming platform. At its core, it is a commit log. Events are written to Kafka and stored durably on disk. Consumers read from Kafka at their own pace. Unlike a traditional message queue, Kafka does not delete events when a consumer reads them. Events persist for a configurable retention period. This means multiple independent consumer services can read the same events without any coordination between them. This is a crucial distinction. In a traditional message queue, a message is consumed once and deleted. In Kafka, a message is written once and consumed by as many services as needed. Kafka organizes events into topics. A topic is a named stream of events. Uber has a topic called driver.location.updates, another called ride.status.changes, another called payment.events. Each topic is an independent event stream. Within each topic, Kafka uses partitions to achieve horizontal scalability. A single topic can be split into dozens or hundreds of partitions. Each partition is stored on a different broker machine in the Kafka cluster. This means Kafka can write and read events in parallel across many machines simultaneously, giving it near-linear horizontal throughput scaling. Consumers are organized into consumer groups. Each partition is consumed by exactly one consumer instance within a consumer group at any time. This automatically distributes processing load across all consumer instances in the group. Here is why this matters for Uber specifically. When the ride dispatch service needs to handle 10 times more events during New Year's Eve peak traffic, they simply add more consumer instances to the consumer group. Kafka automatically rebalances the partition assignments across the larger consumer pool. No configuration changes, no redeployment of producers, just horizontal scale on demand. At Uber's global scale, Kafka handles trillions of events per day. They run Kafka clusters in multiple geographic regions with cross-region replication. This ensures that no event is ever lost, even if an entire region goes dark. Real-time location streaming. This is where Uber's engineering becomes genuinely impressive. Real-time location streaming is one of the most technically demanding pipelines on their entire platform. Let me put the scale into numbers first. Uber has millions of active drivers on the platform during peak hours. Each driver's phone sends a GPS location update every 4 seconds. At peak periods, Uber might have 5 million active drivers sending updates simultaneously. That is 5 million divided by 4. That is 1.25 million location events arriving per second, every second, continuously, with no breaks. Each location event needs to be received, processed, stored, and broadcast to the corresponding rider's app in real time. Riders expect to see the driver's icon moving smoothly on their map. That smoothness requires location updates to arrive and render in under 500 milliseconds, end to end. Here is how the event-driven architecture makes this possible. The driver's phone is the producer. Every 4 seconds, it emits a location event containing the driver ID, the GPS coordinates, the timestamp, the heading, and the current speed. This event is published to Kafka's driver.location.updates topic. That single Kafka topic is consumed by 4 separate downstream services simultaneously. The first consumer is the geo service. This service maintains a real-time index of every driver's current location. It uses a geospatial data structure called a geohash to organize driver positions efficiently. A geohash divides the world into a grid of cells and assigns a short alphanumeric code to each cell. When a rider opens the Uber app and looks for nearby drivers, the geo service queries this index by geohash and returns all drivers within a radius in under 50 milliseconds. The second consumer is the route service. This service tracks whether the assigned driver is following the expected route, continuously recalculates the estimated arrival time based on the driver's actual GPS position versus the planned route, and pushes the updated ETA to the rider's app every time a new location event arrives. The third consumer is the surge pricing engine. Every location event tells the surge engine which geographic zone the driver is currently in. The engine uses this data to maintain a real-time supply count for every zone in the city. We will cover the full surge architecture in the next section. The fourth consumer is the analytics and replay service. This writes location events to long-term storage for historical analysis, route quality auditing, driver behavior analytics, and fraud pattern detection. All 4 consumers process the same stream of events in parallel. Each one scales completely independently. A spike in analytics write load does not touch GeoService query latency. A GeoService slowdown does not affect the route service. This is the operational payoff of event-driven decoupling at real production scale. The surge pricing engine. The surge pricing system is the part of Uber's engineering that most engineers find the most fascinating. And from a pure systems design perspective, it is one of the most elegant real-time stream processing implementations in production anywhere. Let me explain the computation challenge first. Uber divides every city into thousands of geographic microzones. At any given moment, each zone has 2 key numbers: the supply number, which is the count of available drivers inside that zone, and the demand number, which is the count of active ride requests in that zone. The surge multiplier is a function of the ratio between supply and demand. When demand exceeds supply, the multiplier rises. Higher prices reduce the number of ride requests from price-sensitive riders and motivate nearby drivers to reposition into the zone. As drivers enter and supply increases, the multiplier comes back down. This computation has to run continuously for every zone in every city simultaneously, and it has to update in near real time as conditions change second by second across the entire global fleet. Here is the event-driven pipeline that makes it work. The surge pricing engine subscribes to 3 separate Kafka topics simultaneously. The first is the driver.location. The updates topic we already covered. Every location event tells the surge engine that a driver has moved from one geographic zone to another. The engine updates the supply count for the zone the driver left and the zone the driver entered. The second is the ride.requests topic. Every time a rider requests a ride request event is published. The surge engine consumes this stream to track real-time demand building in every zone across every city. The third is the ride.completions topic. When a ride ends, this event tells the surge engine that a driver is available again, and that 1 unit of demand has been fulfilled. Both the supply and demand counts update accordingly. The surge engine processes all 3 streams simultaneously, using Apache Flink for stateful stream processing. Flink maintains the current supply count and demand count for every geographic zone as live state that persists across event processing cycles. Every incoming event from every stream updates this state immediately. When the supply-to-demand ratio in a zone crosses a configured threshold, Flink emits a surge update event to a downstream topic. The pricing service consumes that event and immediately writes the updated multiplier to a distributed in-memory cache. When a rider in that zone requests a price estimate, the app queries the cache and gets the current multiplier in milliseconds. The full pipeline from a driver entering a zone to the updated surge multiplier appearing on a rider's screen takes less than 30 seconds. at global scale, continuously. The driver-rider matching engine. The dispatch and matching system is the heart of Uber's business. It takes an incoming ride request and finds the optimal driver to assign it to, and it has to make that decision in seconds. This sounds straightforward, but at Uber's scale, it is an extraordinarily complex optimization problem. When a rider submits a ride request, Uber is not simply looking for the nearest available driver. They are solving a multi-objective optimization. They need to find a driver who minimizes the pickup time for this specific rider, but they also need to consider the downstream impact of that assignment on other nearby riders. Assigning the closest driver to one rider might leave a cluster of riders in a nearby zone without any driver coverage for the next 30 seconds. That produces a worse outcome for the platform overall, even though it was the locally optimal choice for the individual rider. Uber calls this the batching problem. Instead of assigning drivers to riders one request at a time, they accumulate ride requests over a short window of a few hundred milliseconds. Then, they solve the assignment problem as a batch optimization across all pending requests simultaneously. This produces significantly better outcomes for everyone on the platform, even though any single assignment might not be the absolute fastest possible match in isolation. Here's how this works inside the event-driven system. When a rider submits a ride request, a ride.request.created event is published to Kafka. The dispatch service consumes this event and adds the request to its current matching batch. Every few hundred milliseconds, the dispatch service runs its assignment algorithm. It queries the geo-service for available drivers within a configured search radius. It pulls current ETA estimates from the root service. It runs the optimization and determines the optimal driver-rider pairing for the entire current batch. When an assignment is made, the dispatch service publishes a ride.assigned event to Kafka. The driver notification service consumes this event and sends an immediate push notification to the assigned driver's app. The rider notification service consumes the exact same event and updates the rider's screen with the driver's location and ETA. Both notification services consume the same ride.assigned event in parallel. Neither blocks the other, neither knows the other exists. If the driver does not accept within the timeout window, a ride.assignment.expired event is published automatically. The dispatch service picks it up and returns the rider to the matching pool for the next batch cycle. Every state transition across the entire trip lifecycle is expressed as an event. No service calls another service directly. The entire coordination model is event-driven from end to end. Fault tolerance and resilience patterns. Now, let me cover something that most system design videos skip completely, but that Uber's engineers spent enormous effort on. Fault tolerance. An event-driven architecture is not automatically reliable. The reliability comes from how you design the system to handle failures. And in a distributed system, failures happen constantly. Machines crash. Networks partition. Services run out of memory. Kafka brokers restart during rolling upgrades. The question is never whether failures will happen. The question is whether your architecture absorbs those failures without visible impact to users. Uber implements 3 critical resilience patterns across their event-driven platform. The first is the outbox pattern. When a service needs to emit an event as part of a database transaction, there is a subtle failure mode. The service writes to the database successfully, but then crashes before publishing the event to Kafka. This creates an inconsistency, where the database state has changed, but the event-driven system has no record of it. The outbox pattern solves this elegantly. The service writes the event to an outbox table in the same database transaction as the main data change. The event write and the data write are atomic. Either both succeed or neither does. A separate background process, called the outbox relay, continuously reads from the outbox table and publishes those events to Kafka. Every state change in the database eventually produces a corresponding event in Kafka. Guaranteed. The second pattern is consumer idempotency. Kafka guarantees at least once delivery. In certain failure scenarios, a consumer might receive the same event more than once. If a consumer processes an event successfully, but then crashes before acknowledging it back to Kafka, Kafka will redeliver that event to a new consumer instance on recovery. All of Uber's consumers are designed to be idempotent. Processing the same event twice must produce the same result as processing it once. For a location update, receiving the same GPS coordinate twice simply overwrites the stored position with the same value. no harm. For a payment event, the system checks whether the payment ID has already been processed before attempting a charge. If it has, the duplicate event is acknowledged and discarded. The third pattern is dead letter queues. If a consumer fails to process a specific event after a configured number of retry attempts, that event is moved to a separate dead letter queue topic in Kafka. This prevents a single malformed or unexpected event from blocking the entire consumer indefinitely. The main event stream continues flowing without interruption. Operations teams monitor dead letter queues asynchronously and investigate failed events separately. Together, these three patterns are what makes Uber's event-driven architecture operationally reliable at global scale. Not just functional, but genuinely production-hardened. The complete architecture. Now, let me walk through the entire system, from the moment a rider opens the app to the moment they rate their driver. This end-to-end view shows you how all the pieces connect into one unified, event-driven system. A rider opens the Uber app. The app calls the geo service for a map of nearby available drivers. The geo service queries its real-time geospatial index, which is continuously refreshed by the driver, location, updates Kafka consumer. The map renders with accurate driver positions within 50 milliseconds. The rider requests a ride. A ride.request. Created event is published to Kafka. The search engine has already pre-computed the surge multiplier for the rider zone based on the continuous supply and demand event streams. The ride request is enriched with the current multiplier as it flows through the system. The dispatch service picks up the ride request event and adds it to the current matching batch. Within a few hundred milliseconds, it solves the batch assignment problem and publishes a ride assigned event to Kafka. The driver notification service and the rider notification service both consume that event simultaneously. The driver accepts. A ride.accepted event is published. The root service starts consuming the driver's location events and calculating continuous ETA updates. The rider's app shows the driver moving in real time. Every 4 seconds, a new location event updates the route and ETA displayed on screen. The driver arrives. A ride.driver.arrived event is published. The rider's app displays the arrival notification. The driver taps to start the trip. A ride.started event is published. The root service switches from ETA mode to active trip tracking mode. The ride completes. One ride.completed event is published to Kafka. That single event is consumed by at least 4 downstream services simultaneously. The payment service charges the rider's card. The search engine decrements demand in the zone. The driver analytics service updates the driver's earnings history. The rating service creates pending rating requests for both the rider and the driver. Not a single one of those services called another one directly. Every coordination across the entire trip lifecycle happened through events flowing through Kafka. Loosely coupled, independently scalable, resilient to individual service failures at every step. 4 engineering lessons for your own systems. Let me close with 4 principles from Uber's architecture that you can apply directly to your own distributed systems today. Lesson 1. Event-first thinking. Before designing any feature in a microservices system, ask yourself, what events represent real state changes in this business domain? Design the events first. Design the consumers second. Design the REST APIs last. In Uber's engineering culture, event contracts are treated as the most important interfaces in the system. More important than API signatures. More important than database schemas. When you get your event contracts right, everything downstream becomes straightforward. Lesson 2. Independent scalability. Every service in Uber's system scales based on its own specific load metric. The geo service scales based on location query volume. The search engine scales based on the rate of incoming location events. The notification service scales based on the rate of ride state changes. Because these services are decoupled through Kafka, scaling one never destabilizes another. In your own systems, design each service around a single, clear scaling dimension. What metric drives the load on this service? Let that metric drive your auto-scaling configuration. Lesson 3. Observability over monitoring. In a monolith, monitoring means checking whether the process is up. In an event-driven microservices system, you need richer observability. You need to know how events are flowing through the system. Where is Kafka consumer group lag accumulating? Which services are emitting events at unexpected rates? Which consumers are falling behind their partition assignments? Uber built extensive tooling around Kafka consumer group lag as a leading indicator. When a consumer group starts falling behind, that signal appears minutes before any user experiences any visible degradation. The ability to detect and act on that signal proactively is what separates elite engineering operations from average ones. Lesson 4. Schema evolution as a first-class concern. Your event schemas will change over time. New fields will be added, old fields will be deprecated. When this happens without planning, producers publish events in a format that existing consumers cannot read, and everything breaks. Uber uses Apache Avro with a schema registry to manage schema evolution safely. Every schema version is versioned and registered centrally. Producers and consumers negotiate compatibility through the registry. Schema changes become a managed, non-breaking process instead of a production incident. Let me bring it all together. Uber processes 14 million trips per day by building their entire platform around event-driven architecture. Apache Kafka is the durable streaming backbone connecting every microservice. Apache Flink handles stateful real-time stream processing for complex aggregations like surge pricing. Reliability comes from 3 battle-tested resilience patterns, including the outbox pattern, consumer idempotency, and dead letter queues. The 4 engineering principles you can apply right now are event-first design, per service, independent scalability, observability focused on event flow, and managed schema evolution through a centralized registry. Subscribe right now, because the next video goes even further. We are going to cover AI-powered chaos engineering, how you teach a Kubernetes cluster to detect its own failures and heal itself before a human being even knows a problem occurred. That video is already filmed, and it drops this week. And drop your biggest distributed systems challenge in the comments below. I build this series based on the real engineering problems you are actually facing.